Okay, for geometry today, we're doing 5-2. So we're talking the incenter and the centroid. All right. So like yesterday, we got some similar objectives. First one is we're going to apply the fact that a point lies on the bisector of an angle. What bisector did we look at yesterday? What was it? The perpendicular bisector. Okay, we looked at the perpendicular bisector yesterday. Today we're looking at the bisector of an angle. Again, it's that if and only if, so biconditional, it's equidistant from its sides. So then our other objective is to identify the triangles incenter and centroid. So that's 4 different centers we're going to have. Yesterday we had the orthocenter and the circumcenter. Today we're looking at the incenter and the centroid. All right, we're going to make some related applications. And then we're going to construct, I'm going to put like quotations around this because we're not actually going to construct it the way we should, but we're going to do it like we did yesterday. The triangles incenter. All right, so first up, theorem 5.2.1. A point lies on the bisector of an angle. Okay, so a point lies on the bisector if and only if it's equidistant from its sides. So in the picture, where is the angle bisector? What is the angle bisector? Is which of those lines? Yep, we can call it, okay, good. That's BPQ. That's our angle bisector. Perfect. Okay, so if we look at point P, because this is a biconditional, so it means either way it works. So if we have a point on P, or if we have a point on the angle bisector, we know that it's equidistant from the sides of the angles. Okay, from its equidistance from its sides, so the angle sides. So we know that BP is congruent or equal, it's equal to the length of P to E because the point is on the bisector. Does that make sense? Okay, so what do we know about if Q is also on the bisector? What else? What do we know? A and C. What about A and C? Okay, so this is going to be A Q, right? Okay, so well, we're going to say AQ is equal to, there you go, is equal to QC. You got it. Yes. Okay, we know they're equidistant, so their lengths are equal. Perfect. Okay. Now we're talking about concurrent. The 3 angle bisectors are concurrent, which meant intersecting. We use concurrent when there's 3 or more lines that intersect. We use the word concurrent. So the 3 angle bisectors are concurrent at a point that's equidistant from each side of the triangle. And this is the incenter today. Okay, so that's the incenter. But again, this is from, the incenter is from your angle bisectors. So using this point, the incenter, and the distance to a side, you can construct a circle, and this is called the inscribed circle. Okay, so it's the incenter and the inscribed circle. The reason that they're called this, okay, is because they will always be inside the triangle. The orthocenter and the circumcenter yesterday are not guaranteed to be inside the circle. The only one that's guaranteed to be inside is the incenter. Okay, so I want to look at these points here. Are these 2 triangles down here? And this is where I want your compass. Because we want to make, so this D here is an incenter. So we want to measure from D to one of the vertices, or one of the sides, it doesn't matter which, because that's where it's equidistant, right? Is the radius here. So if you take that measurement, so again, let me turn this. So I'm measuring from the center to one radius, or to one other side. If I could get it lined up again. Oh, I need to make mine a little bigger. Okay, and then we want to inscribe the circle. So we're going to see if we can make our circle in there. If I can get my paper to turn. It gets caught on the wall and the computer and everything else. See, I got off a little bit there. Let me try again. Somehow I totally messed it up. Okay, so let me go back here. Yep, so this circle is inside, I didn't make it very dark, is inside my triangle. That's my inscribed circle. What is it? I was like, my pencil doesn't want to write. The lead wants to fall out, it looks like. I'm having a good old time here. All right, so did you guys get your first one? Sure. Sure? Right? It's so small. I tried to make them a little bigger. All right, then try the next one. Triangle X, YZ, or triangle XYZ. Okay, so measure the radius to set your compass by, right? Measure the radius and then make your inscribed circle. All right, so mine looked a little short here. Somewhere I made a mistake. Oh, because I had my, if I look, my point was above my actual incenter. So that's why my T is off. Doggone. Because the other thing is, what do you notice about these, the inscribed circle? What do you notice about this inscribed circle? Okay, it's hard to draw. Okay, so one, we know it's inside the triangle. And what else did you say? We're not going to call those midpoints. We don't know that they are, but it does touch all the sides. What did the circumscribed angle or circle do yesterday? It went around, yeah. Okay, good. So yesterday the circumscribed angle touched all the vertices. The inscribed angle touches all the sides because it's inside. Awesome. Good job to notice that. Very nice. Okay. Then let's look at this incenter theorem. A triangle's angle bisectors are concurrent, okay, so they're intersecting at the incenter, the point that's equidistant from each side of the triangle. So we're really just restating over and over what I've already said. All right, and so I want you to get one of your triangles out. We're going to do some paper folding today to get the incenter, because I'm hoping that helps us understand, like, actually doing it, how they're different. Okay, so to fold our paper triangle today, we're going to fold one side to another side, but you have to center it through the included vertex, okay? So we're going to fold like these two sides together, okay, because we want it to be centered through the vertex. So this is slightly different than yesterday where we were aligning the bottom of them, the base. This time we're actually like aligning the legs of the angle, okay? Increase that. So what did we just make right here? What is that line? We went from the angle, we took the angle and we cut it in half, we folded it in half. What did we make? That's not a very great line. What is that identified as? What bisector? Not parallel. Nope, perpendicular was yesterday because it had to be perpendicular to the base. What did we bisect? Sorry for the extra noise. What did we bisect? Nope. What did we fold in half? Yes, you do, right here. What did we folded it and we made sure that was cut in half. What is that? Is this a side of my triangle? Is this an angle of my triangle? It's not a right angle. We don't know that it's a right angle. What is it? But is it an angle? Yes, so this is an angle bisector. Okay, that's what I'm saying. So that means this side of my angle is congruent to this side now. All right, so let's do that for all three of our angles. Who knows? Okay, you're doing the other angles. You want to make an angle bisector. You're going to fold it and make each of those angle bisectors. Okay, but again, so this angle is congruent to this angle. Okay, and do your third vertex. So again, you're folding the angle. You're making the sides match up to get your fold perfectly in the middle to get an angle bisector. And so by doing that, making an angle bisector, each side of the angle is congruent to the other side of the angle. Cool, right? You're probably like, no, this is just super nerdy. Thank you. Thank you for saying it's super nerdy. Tearing up my paper. I was going to compare this. Okay. So yesterday, here's yesterday's where we did the perpendicular bisectors, right? But see, it doesn't go up through the vertex. It goes to the side, yes, because it had to be perpendicular to this. Awesome. So this one is called, what is this one called, Lucas? So we did angle bisectors, right? This is an angle bisector. I don't want to write it where you can't read it. This is an angle bisector. But what's the center called? Not the circle is inscribed. That's a good call. I should have drawn a line up here and said inscribed circle. Okay, so look back at our paper fold. If we fold one angle or one side to another side, center through the vertex, we have an angle bisector. We continue with all three sides. We got 3 angle bisectors. The point of concurrency is the incenter, yes. So we're going to label that I, the incenter. And I'm going to flip mine over on the back and I'm going to write incenter on the back so I can have it. But yes, this is the incenter. Hopefully you know that's an I and not an H. I. Okay, we got that, the incenter. Okay, and we could inscribe a circle on this one, but I'm not going to. Because my luck would be it would catch the paper and rip it or something. So that's your incenter. All right, so let's flip over to the back and look at this proof that we have. Okay, because it's the first time you're going to see some of these things. So if we're given triangle XYZ with an angle bisector, so we know that XI is a bisector, so this right here, and YI is an angle bisector. And they've marked that, okay, because they show us that this part is congruent to this part. and this angle is congruent to this angle. Okay, those markings are there. So we want to prove that AI is equal to BI, which is equal to CI, and that ZI, ray ZI, is the angle bisector of angle XZY. So we start with our given stuff, okay, and then we say, well, hey, BI is equal to CI. So this part, right, B to I is equal to C to I. Okay, and we can say that because, and it doesn't look like it in my drawing, it's not the best drawing, but we can say that because any point on an angle bisector is equidistant from the angle sides. And we know this is the angle, or the angle bisector, because we know, or like that this is the point there. Because we know, right, that XI and YI are angle bisectors. So we know this has to be equidistant. Now, why they didn't go ahead and say that AI, like here they said CI is equal to AI as well. I don't know why they didn't go ahead and list all three, but they connect BI to AI with the transitive property here. Are you following me? I mean, I would have thought we could just list all three of them there, but it doesn't. So we'll take it. All right, then the last one is just stating that the segment, or that ray XI, is the angle bisector because, again, any point equidistant from an angle's sides lies on the angle bisector. So if this point, like if we go from Z to I, that is the angle bisector. That line is the angle bisector. Okay, so again, just one for you to see because you might have one, like we'll start seeing some of these using those new theorems in our homework. I know, right? Yay! Okay, so now we're going to switch to a different type. And first we need to know what the median is. What is the median? The middle, right? It's the middle or the midpoint. Okay, so the median of a triangle is the segment that, but so here's the thing, the median of a triangle. Ooh. It extends from a vertex to the midpoint of the opposite side. So this is going to be weird, a little bit weird when it comes to folding it, but then you're going to have this better perception of what that is. So get your last triangle. All right, because it's, like I said, it's kind of a funny one. All right, so I've got my triangle. It says fold a vertex to another vertex and crease the point. Don't crease a line. You're just going to crease that point. That's the midpoint. So take a vertex and another vertex, fold them together and line them up. Okay, and you just want to crease that point, like finger crease that point. You with me? That is your midpoint. Does that make sense? You folded it in half, you got the middle. Okay, now we want to draw a line from the midpoint to the opposite vertex. And that is your median. That should have an N on it. It got cut off. So this is when you need that straight edge. So you're going to draw a line from that midpoint. Okay, so you might even fold your paper back up and to your vertex and line it up. And that's your median. Okay, that's a median. We don't know if it's perpendicular or anything else. We just know it goes from the middle, goes from the midpoint of the side to the vertex of the opposite side. Okay, so we're doing this opposite. Okay, and continue that. So line up, bring your vertices together to find your midpoint. Crease just the edge of that. Okay, open it up and draw your connecting line from your midpoint to your opposite vertex. Whoop, I got off a little bit. Okay, and then do your last one. can't get mine to fold. So bring your vertices together. Do a crease, just crease that midpoint. All right. And now I have my new point, which is called the what? What is that called? The centroid, and we label it G. All right, what do you think about that? No comments? None? So if we look at what we did yesterday, we had our circumcenter. These are all the same triangle. Our orthocenter, the incenter. I don't quite have enough room here. The incenter, and now our centroid. Who knew that a triangle had so many centers? Isn't that kind of crazy? Like all the different ways that you can look at it and adjust it and see the kind of center it has. Okay, now the cool thing about the centroid, some cool things we're going to use. All right, so one, we have the centroid theorem, which says the three medians of a triangle are concurrent at the centroid, which is 2/3. This is the part that's cool. All right, which is 2/3 of the distance from each vertex to the opposite sides midpoints. Like, what does that even mean? Well, here this is in a little bit simpler terms. From the vertex to the centroid equals 2/3 of the entire distance of the median. So in this one, A to G, so this distance equals 2/3 of A to X. Fair enough? Okay. On the next one, we have C to G. C to G equals 2/3 of C to Z. So what's the last one? Let's put it in that box. Okay, but it says from the vertex. So not YG, it's not 2/3, because Y is not a vertex. Not GY, Y is not a vertex of the triangle. B, because right, all the rest of these, A was this vertex down here. C to G, the centroid, that was a vertex. So we need to go from the vertex to the centroid. So BG equals 2/3. Yep, every single one is 2/3. You're following the same thing. Oh, my board has not wanted to write today. It's been very glitchy. So if it doesn't write, it should say 2/3. Two-thirds of what? It's 2/3 of the whole length of the median of BY. Good. So BG would equal 2/3 of the median, so BY. Okay, on to your next sheet. All right, we want to find each length if G is the centroid of triangle PQR and PD equals 15. All right, well, I've done the first one for us, so let's kind of evaluate that one. So we want to find PG, so P to G. Well, that's just what we just did, right? We know that from the vertex to the centroid is 2/3 of the whole thing, right? Of this whole length. So PG is going to equal 2/3 of PD. And I know PD is 15. They told me that. So PG equals 2/3 of 15. PG equals 10. Sweet. All right. How about if we do RG? She's leaving. Okay. All right. Well, I will have this posted online so you can finish it. All right. So how about R to G? What do you think about RG? Would it help to write the same equation like we just wrote for this one? RG, okay, is going to equal 2/3 of what? Not of PD, because RG, it's 2/3 of its median. What's its median? R2. Okay, we don't have to say RG. We just say RF. You're good. All right, so it equals 2/3 of RF. Do we know the length of RF? We don't know the length of RF this time, but look at what we do know. We know GF is 3. So how might we change this? Do we times it? Well, what are you thinking? What are you timesing it by? Okay. 2/3. Why do you think, why would we times it by 2/3? We can only times it by 2/3 if we know the whole distance. Okay. What would you divide? Would you divide, would you divide 3 by something, or what do you think it? Are you trying to fit it into this equation? Okay, but does it fit? It doesn't fit, right? Because we know GF equals 3, but that doesn't go anywhere in our equation. So we might have to change our strategy, which is okay. So just think about this if you have this line. Okay, you have a line, okay, from here to here. That's RF. Does that make sense so far? Okay, and then we have G here, and we know the distance is 3. And we know the whole this distance is 2/3 of the whole. So how much is this? What fraction is this? 1/3. Okay. So if this is 1/3 of the whole, how are we going to find out this part? You don't do anything with the, nope, you wouldn't have to. So this is equal to 1/3. Let me combine these. So in this section is 2/3. So if 1/3 is 3, how big is 2/3? So how long is RG? No, RF. RG. RG is just the 6. Sometimes we do that though. Sometimes we do make it too complicated. And that's why I said, like, let's just look at it if it's a line, right? We can figure that out. All right? Because that's the thing is sometimes we have to take it out of its context. Like the triangle can make it too complex. All right, so let's look at this last one. We want to know EG. We want to find EG. And we know, look at this, we know GQ. I'm going to dash this one, kind of. GQ is equal to 8. So which piece is 2/3? GQ, yes. Okay, so if I think that same concept, just because, like I said, it was a little bit simpler. So we've got E over here, and Q over here, and G here. We know GQ is 8, and that it's 2/3 of the size. So EG is what fraction? 1/3, which is 4. So EG is equal to 4. You made that so simple. Very nice work. All right, so if you've ever talked, have you ever learned about center of gravity? Like balancing anything on its center of gravity? Okay, well, if you had the center of gravity of a triangle is located at its centroid. So if you ever try to balance a, I was trying to think of anything that would have a, like if you had something that was a triangle that had liquid in it, or even a can of soda, you can make it work with a can of soda because the liquid forms a triangle in there. It would balance perpendicular to the centroid. Like right, that's that point where it would balance. It's kind of cool. Anyway, so let's look at the bottom. There's just kind of a summary here between the 4 types of centers that we've looked at because you want to be able to identify them. So the incenter, you're always going to be looking for your angle bisectors. So if it's an incenter, one, it should be labeled I, your center should, or your angles are going to be marked, right? You're going to have an angle bisector. That's a terrible outline, but for the centroid, you're going to have medians. So the sides here, the sides are marked. And it always go, again, it does go through your vertex. All right. For your circumcenter, you're looking for perpendicular bisectors. Okay, so it's bisecting. So these are 90-degree angles. But it's kind of like the median. These sides are equal. Okay, like it cut it in the middle, but it goes vertical. It does not go through the vertex like the centroid does. And the last one that you've got is the altitudes. Okay, so the altitude goes, the altitude goes through the vertex, but it's also perpendicular to the base. So you'll have to be able to recognize which ones are which. Which one gives me an inscribed circle? The incenter, okay, so we might make that note. This is the inscribed circle. That's one way you could check it even. And which one gives you the circumscribed center? Or circumscribed circle? Blah.
Would that be the ovocentre? Or
the circumscribed circle? What's the other one you haven't said yet? It's a yeah, this is the circumcenter, gives you the circumscribed circle. Okay, the inscribed circle, what does it touch? Circle touches what? Uh-huh. The sides. Perfect. Well, that's badass. How about the circumcised circle? All right, good. Yes, the circle touches all the angles. Or you might say vertices. Perfect. All right, good stuff there. All right, that's all I got for you, I think, today. Yep, that's the end of that. So you can go ahead and get started on your homework. Page 217.